Hello and welcome everyone to our webinar Faster and More Reliable MEMS Design with Cloud-Based Multiphysics Simulations. My name is Jukka Kruntinen and I'm the head of marketing at Quanscient, where we have a cloud-based multiphysics simulation software called Quanscient also. In today's webinar, we're indeed going to be focusing on the combination of MEMS design and cloud computing. So in essence, we're taking a look at what's possible with the scaling capabilities provided by cloud computing in MEMS simulations and how it looks like in real life. For this, we have a couple of demonstrations of our own by our team lead of application engineering, Dr. Abhishek Deshmukh, and some real-world customer results from our special guest speaker, founder and CEO of Cogsus and an ex-founder at OnScale, Dr. Andrew Tweedy. Now, let's quickly go through our agenda for some extra details. So, we're actually going to start by looking at some of the challenges faced with simulations in MEMS design caused by the limited computational capabilities and restricted licensing model of traditional simulation software. After that, we're going to see how cloud-based software, namely Quanscient also, addresses these challenges head-on, as well as some other non-obvious benefits of the cloud. Then, as I mentioned, we'll see our first live demonstration from Dr. Deshmukh of a microspeaker simulations with some parametric sweeps, demonstrating the increased design exploration and unique capabilities of the cloud right here live in front of your very eyes. After that, it's time for our guest speaker, who will again showcase some real customer results with Monte Carlo studies of up to 1,000 simulations large. To really see the actual competitive edge you can gain with cloud computing in MEMS, you'll definitely want to stick around for that. After that, it's time for a Q&A session where all of our speakers are here to answer your questions live. We already got some nice questions in our form beforehand, but we'll be addressing live questions as well. And then in the last 5 minutes, we'll do a summary of what we have covered here today and leave you all with the key takeaways. Does that sound good to everyone? If so, let's dive right into the challenges faced with simulation in MEMS and how cloud-based software can address those directly. So to begin, I'm going to assume most people here in the audience are not using cloud-based simulation software yet, but rather have their tools running on their desktops or workstations, so basically their own hardware. That is to say, in most cases, there is a clear and quite imminent upper limit in the computing capacity and random access memory engineers have at hand. Furthermore, the licensing structure is very restricted by nature, limiting the number of concurrent users and therefore simulations. This limited capacity of memory and computing power combined with the restricted licensing model is pretty much the root cause for all of the challenges we're going to present here today. The first and maybe the biggest of them being the need to rely heavily on physical prototypes to validate the designs. As everyone knows, each iteration is expensive and time-consuming, delaying product launches and hindering the response to any manufacturing or reliability issues in the device itself. Next, as MEMS devices by definition involve interactions between multiple physical domains, traditional software can struggle to accurately simulate these complex multiphysics interactions, requiring either simplified models or separate simulations for each domain. This is again by and large due to the limitations in computing capacity and RAM, which can lead to inaccurate results and potential oversights in the design process. Again, with restrictions on the number of licenses and limited computational power, engineers are forced to make design decisions without fully exploring all potential solutions. This can result in suboptimal designs that fail to maximize yield, reliability, or performance, which in turn, again, can increase development costs and delay time to market. Finally, traditional software may struggle to create accurate simulation meshes for the intricate details of MEMS devices. When the model's geometry is exceedingly complex, meshing simply becomes computationally too demanding, if not outright impossible. As a result, engineers have to either simplify the geometry or run multiple simulations on smaller parts and stitch the results together. The results, either way, are suboptimal and at worst lead to costly design iterations and delays time to market. Now, how does cloud-based simulation software address these challenges? And what does that look like in terms of business impact? Let's have a look. So, what cloud computing can allow in theory is next to unlimited computing power and RAM with zero restrictions in terms of licenses. What this means in practice is that engineers can test and validate design variation with faster speed and increased accuracy, reducing the need for extensive physical prototyping. This simply enables shortened development timelines and faster time to market. Now, with the increased computing power, the natively coupled multiphysics algorithms of Quanza and Allsolve enable accurate simulations of even the most complex multiphysics interactions in one single simulation. This again eliminates the need for simplified models or separate simulations for each domain, resulting in a more comprehensive and reliable design validation. Again, with access to the extensive computational resources and faster simulation times, engineers can explore a wider range of design possibilities within the same time frame, allowing for a more thorough optimization process and eventually leading to designs that maximize yield, reliability, and performance. Now, this concept of increased design exploration is actually something our live demonstrations will largely focus on. So, our guest speaker, Dr. Andrew Tweedy, will show how it actually works like in real life application, how it looks like, and what the results and business impact can really be. Finally, creating accurate meshes doesn't have to be a bottleneck with cloud based software. Again, and I'm repeating myself here, but with the immense computing capabilities of the cloud, engineers can create larger, more accurate meshes that capture the full complexity of their designs. Furthermore, the mesh extrusion feature allows generating a high quality mesh even on complex geometries with ease. Let's say ease being in relative terms. As a result, engineers have greater confidence in their simulation results as they are able to better capture the real world behavior of the device, leading to reduced development costs and a faster time to market down the line. Now, before getting started with the actual live demonstrations to see how a cloud based simulation software looks like, and let's very quickly blast through some of the other benefits of cloud based simulation software and their business impact, as I know there will be a lot of interesting stuff for you guys here as well. To begin, we sort of touched on this topic before, but indeed, at least with Kwanzaa and also there are no user limits whatsoever within the platform. This means that any number of engineers, researchers, collaborators can access the platform and view the project, granted you have given the permission, of course. The cloud-based nature of also means that the simulations can be set up and monitored from any device with a web browser, so there are pretty much no hardware requirements. Collaboration also becomes as easy as sharing a link, meaning that team members can work on simulations concurrently, review results, and provide feedback in real time. Now, something our users like a lot is the Python scripting interface, which automatically generates Python scripts that fully define the simulation setup. This gives a lot of flexibility for our users, as we will see in today's demonstrations. Just one example mentioned here is the ability to add physics to the GUI that might not be supported in the GUI. Furthermore, the extensive multiphysics script libraries provide a valuable resource, offering pre-built simulation examples and templates. Then we have the usage-based pricing, which basically means that the pricing is based on the usage rather than the licenses, ensuring that you only pay for the computational resources you use. And on the flip side, when you aren't running any simulations, none of your quota is spent. Yep, this model enables organizations of all sizes to access these powerful simulation capabilities without any huge upfront costs, investments in hardware or software licenses. And finally, we have our praised team of application engineers ready to help customers just a few clicks away in the GUI. In addition, all of our users have access to a comprehensive library of resources, including tutorial videos, documentations, and user guides to quickly learn the software and expand. Now, without further ado, I'll give the stage to the team lead of our application engineering team, Dr. Abhishek Deshmukh, to, as stated, show how a cloud-based multiphysics software actually looks like and how you can achieve the practical benefits mentioned earlier. The stage is yours, Abhishek.
Thank you, Yuka, for the nice introduction and overview on the cloud-based platform that we have. So for today's webinar, I chose my one of my favorite examples, which is the MEMS microspeakers. This is from the open access paper by Melniko and co-workers. MEMS microspeakers are these are basically these emerging technologies. So these are silicon based microspeakers, and they are electrostatically actuated versus the conventional speakers, which use permanent magnets and coils. uh, One of the challenges in the design of these micro speakers is the instabilities and pull in um, uh, uh, unstable equilibrium states that occur, and it's very important to be able to first design the speaker in a way that we avoid these regions of instabilities, so that um, we can cover the wide range of frequency range, basically the human audible range of 20 hertz to 20 kilohertz, uh, with dynamic operation, and at the same time uh, avoid these instabilities. So in this webinar, we'll see how to set up the basic building block of these micro speakers. So this is basically a micro beam attached to uh, clamped on both sides, and near a plate which is fixed, and yeah, across these two plates will be the voltage applied, and we'll see how to set this up in the platform, and also see, as Yuka mentioned, how to set up parametric sweeps to characterize the operational uh, operation of these kind of speakers. So here is a schematic of the setup. In this case, it's shown a symmetry here, but we'll not use symmetry. We'll use full beam. It's a fixed plate at the bottom, and the beam at the top, and um, yeah, and then these are separated by an air gap, operated by voltage across, which is usually a sinusoidal signal. So in this case, I would like to highlight the non-linearities, which are coming from mainly the mechanical motion. So the motion of this beam, which um, yeah, basically needs the mesh deformation and so on, and the electrostatic force, which scales as the square of the voltage. And as I said, the voltage is usually a sinusoidal signal, and if we do some trigonometry math, you can see that ultimately the force acting on this beam would be cosinusoidal, but operating at the twice the frequency of the voltage. And we'll see why this is important, and then we'll also see to be because we want the force at the fundamental frequency, I will use the half the fundamental frequency for the voltage signal in this case. And the quantity of interest here is the total harmonic distortion of the beam at the center of the at the central location, and here's the formula. This is with respect to fundamental harmonic. Yeah, let's jump back directly to the demo. um, to save some time, I already built up some geometry. It's much simpler geometry, basically three boxes. um, i I have used the shared expressions to parameterize my geometry here. So the length about 1000 micrometers, width, and the thickness, and this is the gap between the plate, which I didn't model here on this side, because it's basically fixed and there would be no interesting physics to be model there. So here is the beam, microbeam at the center. On the right hand side, the air gap. On the other side is the free ambient domain. And I also have two shared expressions which we will use later for the parametric sweeps. And to build the geometry, as I said, I use these shared expressions so that I can change them later and have uh, a new geometry, basically to do the geometric sweeps. And this is not the only thing. You can also import your own step file, or also you can directly import the mesh if you have it in certain format. And yeah, with that, let's move on to regular workflow for any simulation softwares. So setting up some properties, then physics and simulation. So let's set up some material properties here, choosing air for the air domain. In this case, we have these two volumes which are consisting of air. Then for the microbeam, I chose monocrystalline silicon. That's the pre-built material in our materials library, but you can also define your own material if needed. Once we have defined the materials, let's go to the physics. uh, we have a list of physics that can be used. For this case, we'll need solid mechanics, electrostatics for actuation, then laminar flow for the fluid flow, and the mesh deformation to take care of the deforming um, boundaries here. Uh, Once we have all the physics added, let's start adding the boundary conditions. So for solid mechanics, we have to clamp the beam from both sides. In this case, let's clamp this end and the other end. Then we have to add the electrostatic force on the beam. Uh, this, you'll see that once we add this for it also appears in electrostatics physics. And lastly, large displacement to take care of the geometric nonlinearities that might appear in the beam. uh, on the electrostatics, we have to add constraints. So let's add the electrode. So the beam acts as the electrode with some sinusoidal voltage. So sine 2 times pi times, as I said, I will use half the fundamental frequency. And as you can see, we already get these shared expressions in the drop down box here to use as a expression for our boundary conditions. And on the other end, we have the surface, this surface which will set the voltage to 0. And again, the electrostatic force is also nonlinear due to displacement, so we have to add the large displacement interaction here. Moving on to laminar flow, first let's set up the no slip boundaries where the velocity will be basically 0. These are the walls of the beam, walls at these fixed plate. Then the ends uh, also um, also on this side and the bottom, and on the other end. Yeah, so these are the no slip boundaries that we have. And as we are simulating the incompressible flow, we need to define the pressure at the outlet. So the outlets would be one here and the other on the end. Yeah, so that's the boundary conditions for the fluid flow. And we have to add one more interaction which between this solid mechanics and fluid, which is fluid structure interaction. And for this, we have to define the surfaces which act as the fluid structure interaction. These are mainly the surfaces of the microbeam on the both side. And again, for these regions where mesh deformation occurs, we have to take care of the large displacement, so the mesh deformation there as well. Once we have defined the physics, we have to also constrain this mesh deformation. So we want to follow the mesh on the solid volumes, so there should be no relative motion between the beam and the mesh. So this should be component of x of displacement, so component of y of displacement again, and component z of displacement. And one more constraint to fix the outer boundaries, so mainly these surfaces which are fixed and they should not move with the mesh motion. Yeah, so all right, so that's all we have to set, and we can move on to setting the simulations. For this example, I already have a pre-created mesh. Here I use the structured meshing because of the relatively simple geometry. It's very simple to set up. For each volume, you can choose three sides which should have which should be divided into different number of segments, and these are matched for each volume, so that the common sides or the common edges have the same number of elements, and with this approach you end up with the structured mesh as shown here. All right, so with that we can move on to simulation settings. Let's add one simulation. uh, Choose multi-harmonic for nonlinear problems, then fundamental frequency, which is available as shared expression. In this case I use 4 harmonics. So we have in all solve we have this 2 and 3 sine and cosine terms, so each of these pairs is one harmonic. So harmonic 1 is the constant part, and 2 and 3 is the harmonic at fundamental frequency, 4 5 at the twice the fundamental, and so on. So in this case I use four harmonics and sufficient number of FFT samples for accurate representation of these waves. Um, for this case, I know that the degrees of freedom is about going to be about 400,000. So I will use about 10 nodes of 16 gigabytes of memory each. We have several nodes here that can be chosen for the simulation, and yeah, and we automatically um, get the I think I forgot to set the volumes here, so let's go back here to preview. Yeah, I need to refresh a bit. So we had to define the solid mechanics region for each of these, otherwise the default is the whole geometry. I defined the interactions but failed to define the regions. For electrostatics we have to choose all of the regions so that it's covering everything. Then the laminar flow is restricted to two volumes, and mesh deformation applies to all volumes. And once we have done that, we get the auto generated Python script where we have several blocks of code uh, for the mesh loading, definition of fields, then definition of boundary conditions or interactions. And here is what Yuka said before about the formulation. So if you would like to add your own models, it's quite easy to do that using these formulations, which are basically the integral weak form of your finite element model. And as you can see as an example here, it's as simple as adding these expressions as you see them in your um, paper or your derivation. And lastly, the call. So this block is for formulations for different physics and their interaction, and lastly this all solve is the call for solution. And for post processing, here we can add our own um, post processing script, so which is based on Python. I have already added this for saving time. I basically copied this from the pre-run simulation. So I can explain briefly. This is the probe. So at this location on the geometry, we are calculating or interpolating the uh, component y of displacement field, and we are interpolating each harmonic. So we have um, in this case for 4 harmonics we have um, 8 components, and which is what I am adding to this list. And to calculate the total harmonic deformation, I have to skip the first harmonic and add up the rest together. And at the end, I am just dividing the sum by the first harmonic and taking the square root. And to get this as an output, we have this function set output value, which will then appear as the single value for each of the parameter sweep in the summary. And the interesting part here is to how to set up the parametric sweeps. So we have here inputs, and you can simply choose the parameter which you would like to use for sweep. For this first, I will choose the frequency range from 20 hertz to 20,000 hertz in 20 steps, and also a voltage sweep, again going from 1 to 20 in the steps of 20. And that's it. That's all you have to do for setting up parametric sweep, and then you can already start this simulation. And once these simulations are finished, you will be able to see the summary here. So it takes a short time to start these jobs here, and meanwhile we can already take a look at the sweep job I ran before. This was exactly set up in the same way. 20 sweep, um, 20 simulations, frequency and voltage sweep. And as I said in the summary, you can get these value outputs, and which you can easily plot um, as a function of frequency or voltage. And this is not just it. When I already ran a bunch of simulations before. So I did the parametric sweep separately for frequencies and voltage. So there will be about 15 frequency steps and the 5 voltage steps, which comes about 75 simulations. And this is what you can see here as a surface plot for the total harmonic distortion. And all these simulations were run at the same time, with 8 cores each, and the maximum simulation time for all of them was about 12 minutes. So within 12 minutes I had the results for 75 simulations, which had 400,000 DOPs each. So yeah, so that's all from my side, and I would like to hand over to Yuka for more interesting stuff from our guest speaker later.
Thank you, Abhishek, for your demonstration. And indeed, next is the moment we have all been waiting for, as I will very soon pass the mic to our special guest speaker, CEO and founder of Coxus, Dr. Andrew Tweedy. Now, Dr. Tweedy's background in MEMS design includes co-founding OnScale and leading R&D at Alba Ultrasound, where he focused on high-performance ultrasonic technologies. At Coxus, Dr. Tweedy has been using Quanta and also to increase the speed of design cycles and product reliability with their various customer projects. Today, we'll get the inside scoop of some of these projects and all of the insights. So, without further ado, I'd like to give a warm welcome to Dr. Andrew Tweedy.
Oh, thanks, Yuka, for that very kind introduction. It's an absolute pleasure to be here to talk to you about really a very interesting area. So I chose to speak about PMUTs particularly because they've been around for a long time, but in the last 10 years, I think the growth and level of interest in PMUTs has been quite remarkable. And I think that's really because it's enabled the integration of ultrasonic technology into quite a range of consumer products. You can see here on the right-hand side of the slide some applications that you'll probably be familiar with. There's a good chance that your smartphone in your pocket has an ultrasonic fingerprint sensor on it these days. TDK have produced a range of 3D sensing devices, which at Cogsys we have a lot of experience working with. And there's been various companies, here we can see Exo Imaging as an example, developing a new generation of biomedical imaging sensors for diagnostic imaging using PMUTs. So a huge interest, and naturally it's an area that our customers are particularly interested in, but it remains a big challenge from a simulation perspective. These are large, typically transient models requiring sometimes tens, sometimes hundreds of millions of degrees of freedom. And it's not a challenge that can easily be handled in every simulation package out there. So what makes them so complex? Well, each sensor in one of these large sensor arrays has quite a complex microstructure with a number of thin layers, sometimes quite detailed interconnects that can be important to capture. And the array itself can comprise potentially thousands of elements. On top of that, there's quite often a large load region in front of the array that can be very important to simulate. So you've got this very large but very detailed sensor coupled to an elastic or acoustic wave propagation region. And there's not a lot of solvers that can handle that all in one simulation. As I mentioned, these are very broadband devices, so it's typically a transient analysis that we want to carry out, and that means solving these tens or hundreds of millions degree of freedom models hundreds or maybe thousands of times. And multiphysics is essential. These are piezoelectric devices. I mentioned the elastic wave propagation. We've got electrostatics. A lot of the multiphysics that you saw Abhishek setting up a moment ago. So at Cogsys, we feel that AllSolve is fairly uniquely positioned to address all of these effects in a single simulation and to do it quickly. And to demonstrate some of the work that we've been doing, we've picked this PMUT fingerprint array example from David Horsley's group at BSAC. A few details here, but it serves as a nice base example to show off some of the things that we do without getting into customer-specific details. So at Cogsys, we like to start with the simplest model possible. The reason we like that is it captures often a lot of the physics and the outputs that we're interested in. But if you can start simple, you can iterate quickly. You can run the sort of design sweeps that Abhishek just showed us. And you can do some other things like the example that we're going to talk about today is Monte Carlo analysis. So it's good to have that base model set up. This is the rectangular PMUT elements that were detailed in the diagram we just saw, and when we run that simulation, we get really a whole host of outputs, the sort of things that we would typically measure in practice when we're evaluating these devices. So on the left, we've got a velocity field, and on the right, we've got electrical measurements of voltage and charge on the electrode. That lets us get really the base performance of this device before we go on to look at more complex effects. And the good thing is that despite being a non-trivial model, I mean, it's just under 400,000 degrees of freedom. There's a lot of packages that would require some quite serious simulation time. We can run this simulation in 4 minutes, which really allows us to iterate very quickly on a new design. So that gives us a good starting point, but to really start to develop a fingerprint imaging array that would perform well in practice, we need to start looking at the array structure and ultimately the inter-element crosstalk, the beam shape, and ultimately the beam forming performance. So this example shows an 11 by 11 section of one of these large arrays. It's been built entirely in the AllSolve UI that you just saw Abhishek using. So a similar process to what he just demonstrated. And we can use that to do a few things. The first thing I want to show here is a simple simulation where we just excite a single element. So we've excited that center element here with a short pulse. And what we can do is observe the crosstalk mechanically propagating out along the surface of the array. I should point out here that we're looking at the array surface in this plot, but the load medium, in this case, a 250 micron region of PDMS, which is quite a light polymer, is still present in the simulation. An aside I could maybe mention there, if I just skip back, the PDMS in this model mimics the paper that we saw on the first slide and is 250 microns. That sounds quite thin, but PDMS is quite slow. So in terms of transit time, that roughly mimics a 1 millimeter sheet of glass. And it was used in the paper to act as a mimic for fingerprint sensing. So in this model, we have that full structure here. And we can see that there is indeed quite tangible crosstalk across the array surface. Now, this is going to affect the imaging performance of the device. It's going to limit beam width. It's going to alter the ability of the array to focus, and ultimately impact our imaging performance. A useful thing to point out at this stage is that this is a much larger model than the one we saw on the last slide. This is 15 million degrees of freedom, just under, over 200 time steps, but we can still evaluate this in under an hour. So it lets us evaluate quite realistic beamforming scenarios where we need to drive the array with multiple different focal laws in really feasible timescales. Here's another example using the same model, but with just different drive conditions. This time we've set it up in a more realistic manner for a fingerprint sensing application where we're exciting a column of elements and we're observing the crosstalk across the surface. And again, this starts to get us to the imaging performance that we would be able to see from this stack. So using that last model, we can dive a little bit deeper. If you look on the right-hand side, you can see the line or the column of elements that you saw me excite in the last video. And the waveforms on the left-hand side are the voltage outputs on the adjacent 4 elements. So you can see from this that there is indeed not just mechanical crosstalk, but voltage crosstalk being observed on the elements. This will affect our receive beamforming capabilities. So it's important to be able to quantify this if we're going to design an effective fingerprint sensor. So that the idea there was to show off some of the things that we do in terms of fingerprint array design and how we would use AllSolve to simulate beamforming performance. But there's another thing that we have started to use simulation for, which is probably more novel, which is looking at the manufacturability of devices. So the next few slides talk about Monte Carlo analysis for PMUT devices. So the question is, why would you do this? Well, as we know, manufacturing processes are all subject to variability, and indeed the materials that we use in those processes vary in properties too. So the performance of any real world device is going to differ from its theoretical simulated performance. And Monte Carlo analysis allows us to simulate this effect and ultimately simulate the effect it will have on the performance of a batch of devices that we build, and ultimately start to give us an idea of what our yield could be. And it's a pretty well-known quote that in manufacturing, yield is money. So there's a lot of device manufacturers are very interested in bringing simulation into their manufacturing engineering departments, where it hasn't really existed in the past. So what you see in the right here is some inputs for our PMUT stack model that we looked at in the first few slides, and we're varying the main dimensions of this simulation. So the cavity width in X and Y, the various thicknesses of the layers. And the histograms that you can see represent a distribution of 1,000 different designs which we simulated. We've set these up by specifying a mean value and then some sort of coefficient of variation around that. And the idea is that this could be matched to the tolerances that we see in our actual manufacturing. And what we want to know is ultimately how will this affect the yield of our manufacturing process. So we can use simulation to do that. Now, just as an aside, to set this up, we've used the Python scripting features that Abhishek mentioned. I find this a really powerful thing where you can use the UI to set up a model in the first instance, but then if I need to add other things or I need to customize outputs and metrics, I can go and edit that script. So I'll skim over this because Abhishek's covered it in some detail. But specifically what we've done here is we've used it to set up those random dimensions. So we've got a line here that goes through the various dimensions that we're interested in and randomizes them using a normal distribution. But what's really nice is that we can set this up once and we can drive it from the design variables that you saw Abhishek setting up. So once this is set up from scripting, we can then use the AI, the UI, sorry, to drive it. So it's nice that we can set it up once and then use the UI at high level. Okay, so when we run 1,000 simulations, what do the results look like? So what we see here is the receive current on our PMUT stack. I could have shown voltage. Current looked a bit nicer to plot in this case. And in all cases, we can see a ring down from the main voltage excitation, but we see a strong reflection in all of the models, and that's from the front face. This is the first return from the front face of the PDMS. But you can immediately see in this rainbow of color that there's a huge amount of variation between these 1,000 simulations. So a nice way to look at this is to pick out some metrics, or what you might call key performance indicators, that you really want to monitor. And in this case, I've picked out the amplitude of the signal and its arrival time. So if we scroll on, we can see a cross plot between peak amplitude and arrival time, and each of the different dimensions that we varied. And the shape of this distribution, without getting into lots of detail on it, tells us a bit about what dimensions are having the biggest effect on the outputs. So there's nothing here that is completely directly affecting everything above all others. But what we saw in this case was that the X dimension of the cavity, which is the shorter dimension of the little rectangle, is having a much more significant effect, particularly on peak amplitude, but also on arrival time, than any of the others. It has a much higher coefficient of correlation. So I think really the final thing to highlight from this slide is we run those 1,000 simulations with 300 time steps each in 15 minutes total runtime. So that again speaks to the capability of the cloud here to accelerate these sort of analyses. And just to cap off, we can present the same data, but in another way. We can show a histogram of those two outputs. So a histogram of peak amplitude and arrival time on the bottom. And we could apply pass-fail criteria to these. So a reference baseline for our theoretical performance, and then upper and lower pass bands. And in a hypothetical example here, we've plugged in some pass and fail values, and we can see that in this analysis, we would achieve a yield of 72%. So these are the sorts of metrics that for manufacturing engineers are very valuable. Increasing that by even a few percent could mean a lot of value, consistency, ultimately profit. So we see this as a big next step in bringing simulations into the field of manufacturing. So with that, I'll wrap up and pass back to Yuka.
Wow, awesome presentation. Thank you so much, Andrew. Now, if you still have time with us, we'd like to keep you for our Q&A session. While we are a bit short on time, we did get some questions beforehand, so let's at least cover those. So the first question for you, Andrew, is from the user perspective, how do you feel about the security of a cloud-based platform?
I think these days when I use cloud for my personal banking, finances, and indeed in Cogsis, we use accounting tools that are cloud-based. We store lots of our data on cloud storage. I don't see it as an issue, and I see the huge benefits that we just talked about in terms of design insights and manufacturing insights as a real motivation to go in that direction. So it doesn't cause us any issues.
Fair enough. Now, another question for you was about the usability. So, and especially getting started. So, how easy was it to get started with Oslo?
Look, I'm fortunate that I've worked in this field for a long time. I found it, so just speaking for myself, I found it very intuitive. I think, to go back to the point I made earlier, the ability to use the UI to set up an initial model and then to be able to see the underlying structure of that in the code and make any changes going forward is hugely beneficial, but also a really useful learning tool for me. So I found that the learning curve not so steep compared to other tools that I've used.
All right. Now, let's take the final question from ourselves. And that question would be, what would you say to engineers hesitant about trying a new simulation software, let alone a cloud-based one?
Yeah, that's a good question. There's a lot of areas, we're bombarded with new tools, new services throughout our daily life these days. And I have to admit, I'm not an early adopter with a lot of these things, despite what appearances may seem. If it works, I tend to leave it alone. Um, I I think that traditional simulation approaches don't do enough. They don't work. And I would say that I would encourage every engineer to at least try this ability that the cloud brings to run massive design sweeps in parallel and get results, very quickly. Speaking as a company that provides consulting services, it's allowed us to turn around projects way quicker than we could have done back in the pre-cloud days. So I understand, people have limited bandwidth and can't adopt everything, but I think this is an area where cloud tools, and particularly also, can make a huge difference.
Awesome. Abhishek, are there any questions in the chat you'd like to answer now?
I don't see many of them, or I don't see questions here.
All right. So if there are any questions you'd like to ask, you can uh, ask them directly from either me or Abhishek on LinkedIn or via email. Yeah, at this point, I'd like to thank our technical speakers, both of you, for your presentations, and again, give a special thank you to our guest speaker, Dr. Andrew Tweedy. Now, before wrapping up, let's go over what we saw here today. So, in the beginning, we established some of the common challenges faced in MEMS design, namely slow prototyping and extended lead times, limited multiphysics capabilities, limited design exploration, and limitations in meshing complex geometries. The main reason for these, as stated in the beginning, is the limitations in hardware. So, in essence, computational power and RAM, as well as license restrictions in the traditional MEMS simulation software. Now, through demonstrations by our technical speakers, we saw how cloud-based software, namely Quanza and also, addresses these challenges through increased computational capacity and zero license limitations to enable accelerated design cycles and reduce reliance on physical prototypes, comprehensive and accurately accurate natively coupled multiphysics simulations, optimized design exploration, and accurate meshing of even complex geometries. Now, as key takeaways, I would summarize that based on what we saw here today, Quantside also enables faster design cycles through faster iterations and increased innovation through the ability to explore a wider range of design possibilities. Now, these would be the big ones we covered in detail. The others, while perhaps less groundbreaking, are still definitely nice to haves, which would be the improved collaboration through the unlimited number of licenses and the nature of the cloud-based platform, reduce onboarding time and increase productivity through the intuitive interface and ease of use, and finally cost savings by eliminating the need for expensive hardware and software licenses, reducing upfront costs and ongoing maintenance expenses. So there we have it. The goal of this webinar was to see how engineers are leveraging cloud computing for faster design cycles and increase product reliability in MEMS design. And I think we have achieved that. Now, if you want to get in touch with us to explore how Quantside also could help with your specific use case, I would highly recommend visiting our website by either scanning the QR code visible on the screen or heading to quantside.com to schedule a 30-minute introductory session with our CRO, Mr. Nicholas Straw. Nicola will be more than happy to discuss your use case with you, basically assess the compatibility of the problems you're facing and the issues you're facing, and take into consideration your existing workflows to not only establish whether Quantside also would be a good fit for you, but to also get an idea of what to expect in terms of results, cost efficiency, onboarding times, etc. After you have a good idea of what the platform can do to you specifically, Nicola will help you get going with the next steps and get you started with results of your own as soon as possible. So again, scan the QR code on the screen or head to quantscience.com and schedule your session. With that, I want to thank each one of you for participating with us here today, and I hope you learned something new. Thanks once again for joining and have a great day. Bye.